Today, I will be presenting a resource on the topic of the Universal Virtual Computer. This presentation is intended to be used as a training resource so that you can adopt the Universal Virtual Computer into your digital preservation workflows as something to add to your digital archivist toolkit. This training presentation hopes to address your concerns about long-term digital preservation by introducing the Universal Virtual Computer to you. We will discuss common issues when preserving obsolete hardware and file formats, the qualities required of authentic digital objects, the development history of the Universal Virtual Computer, how this can be applied to your digital preservation workflow, the advantages and disadvantages of the UVC, and further resources for staying up to date with the UBC and digital preservation. You will likely have encountered digital records stored on obsolete technologies, discontinued or closed source software, and unreadable or corrupted objects. With each new technological advance, digital objects, whose authority relies on their ability to be read and interpreted by a machine, are at increased risk of obsolescence. Data becomes a digital object when it is usable, and also when it satisfies the essential criteria and elements of metadata. But obsolescent technology can corrupt these factors entirely. This obsolete technology often relies upon a chain of dependency to run, but often obsolete technology itself can change the bit stream, corrupt data, make it unopenable, and destroy its authenticity. Record keepers are tasked with preserving these digital objects long term, and the ability to render them in a readable and accessible way is essential. However, as no digital storage medium is permanent, the archivist instead ends up managing the life cycle of the obsolete hardware this is stored on. This is time-consuming, expensive, and relies on future record keepers understanding the obsolete software and hardware. Floppy disks, for example, are often unreadable as their readers go out of production. Increasingly, CDs are also at risk of becoming obsolete, as the lack of a CD drive in modern hardware becomes an increasingly common problem. If it can't be accessed, we risk losing this information altogether. Digital objects must be accessible and authentic. Access to documents in their authentic form may be threatened once the hardware becomes obsolete, even if they were accessible at the time of ingest and even if there are attempts to migrate the software. Even this is prone to structural changes and a loss of authenticity. But to make digital records accessible, record keepers are often met with obstacles such as platform-dependent and proprietary software. It is often the case that born digital material is dependent on the platform it was made for or operates on, remaining open and accessible, and that it retains the documentation and authentication required to open the files. This is not always the case, and support is also often stopped for old systems. Documentation is often outdated, and migration becomes a complicated process with mixed results. Preserving hardware is not always practical for storage, and is not always economically viable or sustainable for a repository, especially with the rate at which hardware and software change. Instead, preserving the ability to run software is much more efficient. Record keepers, in order to preserve born digital documents long term whilst retaining their authenticity and original format, adopted a migration approach and an emulation approach. The Universal Virtual Computer combines both of these methods. The migration approach involves digital objects being copied across different hardware. In the process, this can risk the documents losing their authenticity over time. This also requires the archivist carefully checking each data format for imminent signs of obsolescence, migrating them reliably, and checking that the formatting of these documents has not been compromised. This is time-consuming, resource-intensive, and affects their reliability and usability as original evidentiary documents. The emulation approach imitates obsolete hardware. The digital document's original bit stream is copied exactly, making it authentic and unchanging. Problematically, a new emulator has to be created when the hardware first shows signs of obsolescence. With the rate at which technologies develop, this is a fast-moving and costly process, which can also lead to errors being made in the emulation of these digital objects. But it only needs to be implemented once, and is therefore less time-consuming. The UVC combats the effects of obsolescence on long-term authentic preservation of digital collections that are often in a variety of formats, and turns this into a universal virtual computer that only needs to be designed and applied once. Raymond Lorie created the UVC concept whilst working at IBM Almaden Research Center in 2001. Its objective is to reconstruct digital objects in their original format by combining emulation and migration. Lorie's Universal Virtual Computer is a program which decodes file formats. This method archives the software that is used to render these digital objects, and this, along with the bit stream that represents the document, are loaded into the emulator. The main problem with migrating files, the method, is that the documents need to be transformed and maintained throughout its life cycle. But with UVC, software is rendered before ingest. The more time that is spent developing this software before ingest, the more authentically the document will be rendered. This means less migrations over the record's life cycle and less intervention needed over time by a record keeper. And so, how is this process done? Firstly, digital objects and the programs they operate on need to be archived. This acts as documentation for the Universal Virtual Computer in a way, as it does not just archive the data, but the program it runs on as well, so that the future record keeper just needs to render the UVC as a virtual machine. The format decoder, written before the format becomes obsolete, translates or migrates the digital object, creating a description of its data description. Once this universal virtual computer is created, the program that can run on future hardware will send the encoded data and format decoder to the UVC, and executing this process will create element tags which contain information about the data content and the program that runs it. The element tags build what is called the logical data view, which describes the structure of these element tags. The logical data schema will then provide a description of the information type, such as the RGB color scheme and its relation to a real-world color spectrum, if reconstructing a color image, for example. And then, once fed through a format decoder, this will create a representation of the original digital object, as seen in the image above. The Universal Virtual Computer provides functionality for various data types by preserving digital objects in their original formats after being fed the data through a format decoder. It includes the rules for encoding and decoding this data, which will then interpret the schema for its particular data type. This schema reconstructs the meaning of the tags, which for the viewer reconstructs a digital object, making it readable and accessible. By keeping the bit stream of the document intact, the UVC interprets its logical structure and allows its interactivity, making the document scrollable, searchable, and easy to navigate. Krebs, Schmitz, and Borghoff ran an experiment to test the potential of the UVC's long-term application and implementation, with hardware including supercomputers, vectors, and parallel computers and desktops. They proposed a singular standard of representation numbers which reduced the probability of implementation errors and improved the execution speed. On the one hand, Universal Virtual Computer is very successful at preserving the authenticity and integrity of the digital object. It promotes access and functionality independent of the hardware it is operating on, as only the UVC has to be emulated and minimal code revisions are needed. It is free, and the UVC's simple architecture uses just 25 instructions, an unlimited amount of bitwise accessible memory, and unlimited registers. meaning it is very flexible. But alternatively, there are some negatives. It may require some programming skills and computing knowledge to implement, and work needs to be done to make it more user-friendly. Its long-term efficiency as a computer is not guaranteed. Its functionality in the future is also difficult to predict. Preserving active documents through parallel processing could risk the authentic preservation of these objects. It can be expensive to upkeep even though it is free to install. The implementation of it varies in the time it takes to effectively produce results. To become a more effective tool for record keepers, more training should be available. Currently, it provides a certain level of expertise that those beginning their digital preservation process may not have access to yet. It needs to cover more file formats. There needs to be more research done into ways the UVC can help preserve dynamic content and data such as user interaction. I would recommend that record keepers implement other tools alongside this that can track the organization's digital preservation capability, including the documentation required to run the UVC in the future. Examples include the Digital Preservation Capability Rapid Assessment Model. Fast implementation times require a higher programming skill. If working with a computer scientist, you may need to communicate the FAIR principles to them to ensure that they understand the requirements of your archive's data. I hope this training resource has been helpful and given ways that the UVC can be implemented into a digital preservation workflow. Here is a bibliography of resources if you would like to find out more about how to use and install Universal Virtual Computer.